Good afternoon, everyone. This is Microprocessor and Microcontrollers, subject code 15CS44 for the Computer Science and Information Science Department students. This is Module 5, Introduction to ARM Instruction Set. My name is Harish V. Mikli. I am from BMS College of Engineering. Let's see the syllabus again. In the introduction to, this is module 5, okay, module 5, introduction to ARM instruction set. In that, data processing instructions, branch instructions, program status register instructions, load store instructions, software interrupt instructions. Till here we have covered, or we have covered in the last class. Today we need to cover coprocessor instructions, loading constants, and we will try to see, if time permits, the simple programming exercise on these instructions. For this, textbook 2 mentioned in the syllabus, and this is from chapter 3 in that textbook 2. So, previous lecture we have covered the ARM instruction syntax and the whole chapter is about ARM architecture version 4T, ARM 7, in that ARM architecture version 4T, in that ARM 7 TDMI family of processors. That too we are discussing in particularly ARM state. The ARM instruction syntax again goes like this: label, instruction, CC, condition, yes for updating CPSR, operand destination operand, source operand 1, source operand 2, and ball shifter operations. The thing that the details that are mentioned in this flower bracket are optional. In that, like when we go to the ARM instruction set, the ARM instruction set can be classified into data processing instruction. In data processing instruction, data movement, arithmetic, logical, comparison, and multiply instructions, branch instructions, program status register instruction, load store instruction, and software interrupt instructions. Till here we have studied, or we have studied in the last class. What we do today, agenda for today's lecture: coprocessor instructions, loading constants, and summary of ARM instruction set. With these three-point agenda, we will follow the lecture today. Let's start with coprocessor instructions. Before getting into the coprocessor instructions, what do you mean by coprocessor? Coprocessor is a companion to an existing ARM processor core, which will extend its ability to compute or to control. Both the options are possible. One such example: the basic ARM core does not perform any floating point operation. So, there is a separate coprocessor that performs a floating point operation. So, you can combine the existing ARM processor core with a coprocessor core to get the floating point operations. And there are also the coprocessors for memory management. If the memory is expanded, if the cache is expanded, if the RAM is expanded, then like we need a memory management unit. For that, we require a separate coprocessor which will handle this memory units. So, coprocessors, in any processors for that matter, coprocessors are required to extend the ability to compute, or to ability to control, the ability to control. In here, the most of the instructions are coprocessor specific, but some instructions work between ARM processor core and coprocessor. Few of them are mentioned below. So that's the second point. What do you mean by this second point? Most of the coprocessor instructions are meant to execute on a coprocessor. So we cannot take particular examples in detail in here, because there are around 15 to 20 coprocessors available which will work in companion with a basic ARM processor core. If we select one of these coprocessor, then we can discuss on the instruction set. But there are some instructions which are in general to work between the existing ARM processor core and the coprocessor So these instructions, or in this few instructions, we will discuss. What are these instructions? Instruction 1 is CDP. What is CDP stands for? Coprocessor data processing instruction. It performs an operation on a coprocessor. Now, every instruction that executes on the ARM, every instruction that need to execute on the coprocessor, first it comes to the ARM processor core. Then the processor core decides it is not meant for itself, it is meant for the coprocessor. Then it transfers that instruction to coprocessor. This is the functionality. So CDP, the coprocessor data processing instruction. MRC or MCR, coprocessor register transfer, move data from coprocessor registers to the main processor core, or from main processor core to the coprocessor registers. LDC and STC, coprocessor memory transfer, that is, these are load store instructions which works between the coprocessor and the memory. That's what this statement says. Coprocessor memory transfer, load and store blocks of memory to or from a coprocessor. Now let's take a look at the syntax of these instructions. CDP, condition, CP, opcode 1, opcode 1, CD, CN, comma, in flower bracket, opcode 2. That means this opcode 2 is an optional one. The second one, MRC or MCR, one of this instruction with a condition, CP, opcode 1, RD, CN, CM, again in the flower bracket, opcode 2. Again in here the opcode 2 is an optional thing. LDC or STC, one of this instruction, condition, CP, CD, addressing modes. In this, what are this CP stands for? CP is for coprocessor number. For example, there are around 16 coprocessors for ARM 7 family of processors, or ARM 7 TDMI family of processors. These coprocessors numbered from CP0 to CP15. So that processor number you have to mention in the first operand of the instruction, first operand of any instruction. That is what CP stands for. CP stands for coprocessor number in the instruction here. Opcode 1, operations to take place on a coprocessor. This opcode 1 here is indicated by a processor core to the coprocessor, saying that like this is the operation that coprocessor has to do. CD is a coprocessor destination register, CN is a coprocessor primary register, CM is a coprocessor secondary register, or it is also called, sometimes it is also called as an extended register. Opcode 2, which is optional in the first two instruction, which is said as optional in the first two instruction, is a secondary register modifier instruction. That means this opcode 2 works only on CM or CM instruction or CM register, that is secondary register. So that's the syntax and the details of the syntax. What we do is like most of these instructions are very generic, so we will take one particular example and try to explain this. Coprocessor 15, that is P15, is called as a system control processor. What is its functions? Its functions are memory management, it manages the memory, write buffer control, cache control, and identification registers. So this coprocessor 15 or P15 is a coprocessor to do the system control option. System control in the sense, in particularly the memory management. It also, in the memory management, it manages the write option, write operation to the buffer, cache it also controls the cache memory. It has some identification register. In that identification register, register C0, which contains coprocessor identification number, with which the main processor core identifies what kind of coprocessor has been attached to it. Now what we do, we will take one example in this, that like copy the content of register C0. As we said in the previous, register C0 holds the coprocessor identification number. Coprocessor register C0 from coprocessor 15 to R10 of a ARM processor core. If we want to copy the coprocessor number from register C0 to the main processor, ARM processor core register R10, then what is the instruction? The instruction is this one, MRC P15. P15 is coprocessor number. 0 stands for opcode 1, which is 0. Please see to the previous slide here. That is CP is P15, opcode 1 here in that position we are mentioning 0. Next we are mentioning R10. R10 is for register, destination register for ARM processor from the ARM processor core. Then like C0 is a primary register in the coprocessor. Again the C0 is also a second register, but that secondary register on which we are not doing any operation. That's why the last operand is also 0. The last operand in this is opcode 2. Let's repeat this example. MRC P15, 0, R10, C0, C0, 0. Both the zeros says that operand opcode for a coprocessor is nothing. We are not instructing the coprocessor to do anything. We are just instructing a coprocessor 15 to copy the content of C0 register to R10 register. R10 register belongs to ARM processor core. C0 register belongs to coprocessor register C0. That C0 contains coprocessor number with which the main ARM processor will understand what is the nature of the coprocessor. This is a small introduction to the coprocessor instruction, and this small introduction is there in the syllabus. So that's, we will conclude with the coprocessor discussion, that like in the coprocessor there are 3 instructions: CDP, MRC or MCR, LDC or STC. I can say in total coprocessor instructions are 5. We will see to that in the summary again. Let's look at the loading constants. The another type of the instruction, or a last classification of the instruction in ARM processor core, is loading constants. How do we load a constants? First point to remember, or like first point says in this slide, there is no ARM instruction that moves 32-bit constant value to the register. Whatever we have studied as an instruction, data transfer instruction as MOV and MVN, those instructions cannot move 32-bit constant value to the register. Why? The second point, see to the second point. This is because ARM instructions are 32-bit in size, and hence they cannot encode 32-bit value in an instruction. So ARM instruction itself is a 32-bit instruction. In that, the immediate value, for the immediate value, the maximum bit in the 32-bit instruction for an immediate value is 12 bits, right? In that, 4 bits are reserved for rotate operation and 8 bits are reserved for opcode immediate value. So I will repeat again what is this statement says. There is no ARM instruction that moves 32-bit constant value to the register. This is because ARM instructions are 32-bit in size, and hence they cannot encode 32-bit value in the 32-bit instruction itself. This is obvious statement. 32-bit value cannot be encoded in the 32-bit instruction because we need some space to encode the instruction itself. Hence, we cannot push 32-bit value or immediate value in the instruction. So what in that, like, what is the option that we have? Okay, one more point it is there, that like in general the maximum immediate value that we can move to a register using move instruction is 8-bit value only. That means you can write the instruction as, see to the example 1, move R0 comma hash 0x 6 zeros followed by FF. If you write this, it works. If you increase one more F here, that is 5 zeros followed by 3 F's, F, 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 then the instruction will not work, because in the 32-bit instruction only 8 bits are meant for immediate value. That is what the second example says. MOV R0 comma 0x F, 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 all 8 F's. If you give that value, it does not work. So what is the method to work on this? There is one method using which we can solve this problem, that is use the instruction MVN in place of MOV, because you want to move all the bits you want to make 1, then like use the instruction MVN R0 comma hash 000. If we do this, MVN, as we all know, move negate thing, that means it takes 1's complement value of this immediate value. So 1's complement of all zeros is all F's, hence we can move register R0 all F value using an instruction MVN. There is also another method. See, this is a one simple exercise that like we can do, but we cannot push all the values again using this MVN instruction. So we have one instruction called as LDR to do this. There is a similar instruction to load register, but this instruction in here is a pseudo instruction. Or what do you mean by pseudo instruction? We will see that in the next slide. To conclude this slide, what it says is that there is no ARM instruction that moves 32-bit constant value to the register. We cannot move 32-bit value to the register directly. So what is the option that we cannot move that? That is because ARM instruction by itself is a 32-bit. In that 32-bit, we cannot encode the another 32-bit value itself, because we need some space for opcode encoding, operation encoding. Hence, altogether, the in 32-bit instruction, 8 bits are reserved for immediate value and the 4 bits are reserved for rotate operation. Together, the maximum 12 bits can be used there. More than that, you cannot use. That is what the example 1 says. Example 1, move R0 comma FF works, but move R0, example 2, move R0 comma 0x hash move R0 comma hash 0x 8Fs will not work, because it is more than 8-bit. To do that, we have a one instruction called a LDR. LDR instruction is very similar to the load register instruction in the previous load and store discussion, but in here it acts as a pseudo instruction. What do you mean by that? We will see in the next slide. Syntax for LDR is LDR RD comma equal to constant. We will see this, what do you mean by equal to constant with the example. There is one more instruction called ADR, ADR RD comma label. What it does? LDR is load constant, load a register value RD with some constant value. ADR is load address, that is load register RD with some relative address to the with some relative address. What do we mean by this thing? We will study in the next discussion. See to this thing. If I say LDR R0 comma equal to 0xFF in my program, actually what happens internally is it gets converted to the instruction MOV R0 comma hash 0xFF, because FF is a 8-bit value. 8-bit value. So that 8-bit value can be moved to a register R0 using the instruction move. Now, if the instruction is, if the immediate value is more than 8-bit, we can still mention the instruction LDR R0 comma equal to 0x 8 5s, 8 5 5 5 5, totally 8 5s. Then the internally it is gets converted to this thing. What is that? LDR R0 comma in square bracket PC comma hash offset underscore 12. That means PC plus 12 bits of offset. That's the meaning of this PC comma hash offset underscore 12. So what happens in this particularly, or like what do you mean by, if I write this instruction LDR R0 comma equal to 0x85s, then like internally it gets converted to the LDR R0 comma this value. This means if a programmer uses this instruction LDR R0 comma equal to 0x555585s, then like the assembler which is responsible for converting this mnemonic or this instruction to the opcode, the basic opcode, that converts this instruction internally to the LDR R0 comma in square bracket PC plus offset value. What is the exact, how exactly it is used or how exactly it works, we will see in the next slide. Before going to the next slide, we will see this ADR instruction. ADR instruction is for loading the address. If we want to copy an address of certain labels onto some register, then we should use this instruction. ADR R7 comma label is an instruction. What happens internally? Internally in the sense like the assembler will convert this instruction to the ADD R7 comma PC comma offset. That means PC and offset will add together and that value gets copied to the R7. What is this offset meaning? Again we will see to that in the next slide. And whatever we say here as actual instruction and the pseudo instruction. Pseudo instructions are used or written by a programmer. Actual instructions, a programmer or you yourself can see this actual instruction after writing this pseudo instruction in a disassembly window of the Keel software. We will see to that in coming classes. But right now, please note that, or to conclude this slide, there are two loading constant instructions. One is LDR, another is ADR. LDR is for loading the constant, ADR is for loading the address. These both of these instructions are pseudo instructions. That means these instructions can be used by the programmer, but internally they gets converted to some other instructions. That example is shown below here. If we use LDR instruction, LDR R0 comma equal to 0xFF, it is a 8-bit value getting copied to R0. Hence, internally the assembler converts this instruction to move R0 comma hash 0xFF. If we try to do more value, or like we'll with example 2 here, LDR R0 comma equal to 0x followed by 8 5s, then that instruction gets converted to LDR R0 comma in bracket PC comma hash offset 12. This is about the LDR instruction. ADR instruction, for ADR R7 comma label, that if we want the address of this label on this register R7, then like if we write ADR R7 comma label, internally our assembler converts that to the add R7 comma PC comma offset. Offset value gets added with PC, existing PC value. That PC value is copied to the R7 here. Let's see both of this instruction LDR and ADR with an examples in the next slide. See to this, what we can write or how we can use this instruction in the programming. ADR R7 comma stop. Stop here is a label used for branch instruction here. If we, after this ADR R7 comma stop, we are just using two move instructions, MOV R7 comma hash 2, that is R7 gets a value 2. MOV R2 comma hash FF, that R2 value register R2 gets a value FF. The last instruction is stop, B stop. If you remember this B, it is just a branch instruction. What happens here is B stop, the jump happens to the head itself. So, the label points to the branch, label points to its head itself. So, it keeps jumping in this. So, the further instruction will not be executed if we use this instruction stop, B stop. If there is any instruction after this, it will not be executed, because this is very similar to unconditional jump from tail to head, and it continues infinitely. It is just like while one or while one condition in the C program. So, what is happening in this total? Internally, if we use an instruction ADR R7, stop, this stop is replaced by PC value plus offset. PC value here will be the address of move R7 instruction. From there, the offset is plus 4. If we add the existing PC value plus 4, we will get the label address, that is stop label address in stop label address, and using this instruction that address gets copied to R7. So, R7 gets a value PC plus 4 thing. So, I look at the example 2. In example 2, the example 1 is for ADR instruction, example 2 is for LDR instruction. In here, we have written this with already a kind of disassembly thing. What will be the instruction for this? LDR, R0. See to the previous slide. LDR, R0, some higher value is pushed. What is that higher value? It is just like 0x55555, that is 8 5s. If we write an instruction LDR, R0, equal to 0x555, then that gets replaced by this instruction. What is this instruction? LDR R0, in square bracket PC, hash constant number PC value. That means where that constant number is stored. After that, there are two instructions, move R7 hash 2, and then the move R2, hash FF. That is R2 gets a value FF, R7 gets a value 2. After that, there is a constant underscore number. For that, we have defined a DCD 0x5555, 8 5s, that get assigned to constant number. That constant number value means memory location of that constant number will be given to this instruction, that gets added to PC. That whole will form an address where this 0x85 is stored. From there, from that address, this 0x85's value is fetched and then loaded to register R0. So that's what happens when we say LDR R0, equal to 0x85. Assembler internally converts that to this instruction. So both of this instruction, LDR and ADR, both of these instructions are pseudo instruction. They by themselves do not have a direct opcode value. They gets converted to the some other instruction. That conversion is done by an assembler depending on understanding of an ARM processor core. So once this gets converted, for that the opcode is generated and then it is executed onto the ARM processor core. That's why we call ADR and LDR loading constant values instructions as pseudo instructions. With this two examples, we will conclude the classification of ARM instruction set. That is, in today's class, we have discussed coprocessor instructions and loading constant values to the registers. So, all the classification of instructions has been discussed. Before taking a leave from this class, we will just glance what we have studied in the previous all these 5 lectures. This is a very standard slide which links an ARM processor core and a memory to all the instruction sets. Let's look at this for a minute. First thing, this is a ARM RAM memory and this is an ARM processor core, right? ARM processor core. From ARM processor core, we will generate an address, that is RAM location. From that RAM location, the value is copied to the register file. This operation is called as load operation. To do the load operation, we have the instruction LDR that supports 32-bit, LDRH that supports loading of 16-bit value, LDRB that supports loading of 8-bit value, LDM that is load multiple register and in a single instruction or using a single instructions. Apart from these four, there are another two instructions which will work with this sign extended block to load the instructions, load the values to the registers. What are these two instructions? LDRSB that is load register signed byte, LDRSH that is load register signed half word. These instructions 4 plus 2 instructions, 6 instructions are used for loading the RAM content to the register file. And there are some instructions which will help us to store this register values onto the RAM location. Those instructions we call it as a store instructions. These store instructions are STR that helps in storing the 32-bit value, STRH that helps in storing the 16-bit value, STRB that helps in storing the that helps in storing the 8-bit value from a register to the RAM location. Then there is an STM instruction that is store multiple registers onto the RAM memory location. With these four, there are two more instructions called as SWP and SWPB. These two instructions we have discussed yesterday. These are swap and swap a byte. Swap the register value with the RAM location value. Swap the values. First point. The second one, swap a byte. Swap the lowest byte of the register with a memory location. Swap the content. So these all the instructions work for loading the value from RAM location to register or copying the register value to the RAM memory content. And that's why, and these are the only instructions which will work on the memory RAM memory location. All other instructions will just work with a register file content. That is why this ARM architecture is called as a load store architecture. See to the next one. Next one in here, the red label above the register file block is, it supports, for register files it supports the move instruction, MOV, MVN, LDR, ADR, MRS and MSR. Move instruction is directly moving some value to the register, from register to one more register, or like from to a register to the new immediate value. MVN is move the value with one's complement value of the source operand to the destination operand. LDR, here the LDR instruction is for moving the 32-bit constant value to the register file. ADR instruction is for moving the label address to the registers. MRS instruction is for copying the register content to the CPSR. MSR instruction is for copying the CPSR content to the register. So all these instructions are associated with the register file, because even the CPSR register is one of the register in this register file. Now there are some instructions which are associated with ALU. ALU is a heart of the processor core, which is arithmetic and logical in it. It performs all the arithmetic and logical instructions, or it will execute all the arithmetic and logical instruction except the multiply and accumulate instruction that we will discuss in the next point. Right now, what are the instructions that is executed on the ALU, or that's directly supported by ALU? There are some logical instructions like AND, ORR, COR, BIC. These four logical instructions are supported by the logical unit of ALU. ADD, ADC, SUB, SUBB, RSB, RSC are supported by arithmetic unit of the ALU, and there are some instructions like CMP, CMN, TST and TEQ. These are supported by the with the help of logical part and arithmetic part. These instructions are executed. These last 4 instructions are comparative instructions. So what this does, we'll check from the first one. AND instruction is for logical AND operation, bitwise logical AND operation. ORR instruction is for bitwise logical OR operation. EOR operation is for bitwise logical XOR operation. BIC is for bit clear. If we want to mask any bits in the registers or in the port that we will handle, then like BIC instruction is very widely used. ADD is for addition, ADC is addition with carry, SUB is subtraction, SUBB is subtraction with borrow. RSB is reverse subtraction, that is source operand 2 minus 1 will happen. RSC is reverse subtraction with carry. And then like CMP is compare instruction internally get executed with the help of SUB instruction. Compare the negate is the instruction that executes with the help of ADD instruction. TST is for test a bit, test for the bit. TEQ is for test for equality. So test for bit will execute, or TST instruction will execute with the help of AND instruction. TEQ instruction will execute with the help of EOR instruction. What is the point that we need to remember in the compare instruction? Compare instructions do not update the destination register, or destination register in here itself is a CPSR itself. So they affect only the CPSR register. Then there are other instructions in the execution instruction. Those are connected to the MAC unit. These MAC unit execute multiply instruction, MUL, MLA instruction, that is multiply and accumulate instruction. And these two instructions are meant for 32-bit resultant operation. That means if the result is 32-bit, if the result is expected to be 32-bit, then we will use MUL and MLA instruction. If the result is more than 32-bit, then we need the two registers to be combined to hold the 64-bit result. In such a case, we use two instructions, UMULL, that is unsigned multiply long, UMLAL, that is unsigned multiply and accumulate long. These two instructions again are only for unsigned operations. If we want to do a signed operation, then there are two more instructions, SMULL, that is signed multiply long, and SMLAL, that is signed multiply long and signed multiply and accumulate long. So last two instructions are for signed operation. The remaining four instructions are unsigned operation, which will execute on the MAC unit of the processor core. Next, we will see this instruction which will help us to do the branch, or like to discontinue the sequential flow of the program. Those are the branch instructions. Whenever a branch instruction need to be executed, the PC value cannot be just like a PC plus 1 or PC plus 4. So it has to be updated with the help of ALU. In such a case, finally, this branch instruction will update the address register, which will access the next executable instruction from the ROM location. These branch instructions are B. B stands for just branch. This is a just B instruction is a non-conditional. It is very similar to a non-conditional jump instruction in any other processor. That B instruction can also be combined with the condition code that makes it as a jump instruction with condition. Now the next instruction is BL, that is branch with link. What it is meaning? It is very similar to the call instruction in other processor. What do you mean by branch with link? It stores next possible, next executable instruction address, that is PC value, onto the link register before branching. The next two instructions are BX and BLX. Both of these instructions are very similar to B and BLA, but they are widely used for changing the processor state from ARM to thumb, thumb to ARM, and then like doing the branch internal to that. There is one more instruction called SWI. SWI is a software interrupt instruction. This is also a kind of a branch instruction, but SWI instruction is a software instruction or interrupt instruction, which is nothing but again software exception handling instruction, which helps us to call the operating system routine from the user mode. Whenever we use instruction SWI, it forces the ARM processor mode from the user mode. If it is in the user mode, then it forces it to go to the supervisory mode, that is from unprivileged mode to the privileged mode. Then there are some instructions which are supported by the coprocessor, that we have, whatever we have discussed in today's lecture, that is CDP, MRC, MCR, LDC and STC. LDC and STC is to load the memory content to the coprocessor register. MRC and MCR is to copy the coprocessor register to the main register, main processor core register, or copy the main processor core register to the coprocessor. CDP is a data processing operation on the coprocessor. So these are all the instructions. This slide indicates this red patches as a set of instructions executed on the blocks of the ARM architecture. That this is a very important slide for the ARM instruction study. Let's look at the final slide for the unit 5 or module 5. In that we have studied 7 different data processing instructions, or 7 different 7 classification of the instruction. In that we have data processing instructions. There are 22 data processing instructions that we have studied. Data movement instruction, there are 2 data movement instructions that we have studied, MOV and MVN. There are 4 logical instructions that we have studied, AND, ORR, EOR and BIC. There are 6 arithmetic instructions that we have studied, ADD, ADC, SUB, SUBB, RSB and RSC. There are 4 compare instructions that we have studied, CMP, CMN, TST and TEQ. There are 6 multiply instructions that we have studied, MUL and MLA, UMULL, UMLAL, SMULL, SMLAL. There are 4, okay, these are all the instructions which comes under the data processing instruction. Together all this, it will become 22 instructions. Next class of instruction is a branch instruction. There are 4 branch instructions which are supported by ARM architecture version 4T. These are instruction B, BL, BX and BLX. And there are 12 load store instructions that are supported, that is LDR, STR, LDRH, STRH, LDRB, STRB, LDRSB, LDRSH, LDM instruction, STM instruction, SWP for swap, SWPB is a swap of byte. Then there are software interrupt instruction. There is only one software interrupt instruction, that is SWI. Every SWI is instruction is associated with a SWI number. That number is the one which decides like what kind of service routine has to be executed. Now 5th class of instruction is program status instruction. This is like how do we copy the content of CPSR register to the general purpose registers or general purpose register back to the CPSR. There are 2 instructions, MSR and MRS. And there are 5 coprocessor instructions that we studied in the today's class, CDP, MCR, MRC, LDC and STC. And then like at the last we have studied a loading constant instructions, that is LDR and ADR. There are 2 instructions that are LDR and ADR. All together totally there are 48 instructions that we have studied. So till today, that like in the last, including today's lecture, in the last 5 lectures, I am saying including today's lecture, we have studied 48 instructions of ARM architecture version 4T, supported by ARM processor 7 ARM 7 TDMI, ARM 7 TDMI family of processors in ARM state. There are separate instructions which are executed in the thumb state, which we have not studied in today's in these classes, and that those are also not covered in your syllabus. So in total, to conclude, what we have studied in today's class: coprocessor instructions, loading constants or instruction that supports loading the constant value. We have studied the instruction set with an architecture, and we have studied the number of instructions in the instruction set with the instruction set classification, and then we have studied an ARM instruction summary of ARM instruction set. So in the last 5 lectures, we have studied ARM instruction set and what is the instruction, what is the ARM instruction processor core, how it supports an execution of instruction, what is the syntax of ARM instruction, and what are the classification of ARM instruction set, that is data processing instruction, branch instruction, program status register instruction, load store instruction, software interrupt instruction, coprocessor instruction, and loading constants. If there is any doubt regarding this 5 lectures, you can contact me on this email ID or the phone number. If there is, this concludes the theoretical part of the unit 5 or module 5. From the next class, we will concentrate on the programs in assembly level language and the programs in the the programs that can be executed using the C language. So in the next class, we will focus in particular to the assembly level language. I request or I wish all of you should become a little bit familiar with the Keel software before coming to a next class. We will use the Keel software with all the instruction set, and that particularly I wish or I request all of you to look at this slide or have this slide next to you when you write first programs. Then like gradually we can get familiarized, then like we can be an expert on ARM program writing or programs, writing a program on ARM processor core. So if there is any doubt, please contact me on this mail ID and this phone number. Thank you so much.